So we're going to talk about rotational motion. Why would you care about rotational motion, you ask? Because sometimes things spin. These are things like CDs, power tools, merry-go-rounds, yourself if you get too bored in a chair in lab. All these things spin. So let's take a look at this. So when you're looking at angular quantities, we're looking at how much this angle changes. To go, let's say you go from this part and you're going this way. This would be some angle theta. So if you run around this circle, and let's say you have a smaller circle too, if you go from this point to this point, you still go an angle of theta. So it's just how much of a circle you make. All right. Now the other thing to note is that theta is measured in radians, and we'll just abbreviate that rad, making it the coolest unit in all of physics. That's a horrible joke. But anyway, so theta is in radians, and you'll know that one complete revolution, 360 degrees, equals 2 pi radians. Now you do not, I repeat, don't put your calculator in radians. So don't put your calculator in radians. All right, you don't need to mess with it. But what we're interested in is how do we relate this angle to how far you move around the outside. So if we want to relate the radius of the circle to this distance s, we're going to find out that s, the distance you go around a circle, is equal to r times theta. If you go all the way around the circle, this would be s equals 2 pi times radius, which is circumference, which is what you would expect. So now let's take a look at what we do. If you look at what we'll call angular velocity, it's omega. And angular velocity is in radians per second, which means how fast is theta changing? How quickly are you spinning in a circle? So if you have some velocity going this way and some velocity going this way, you know that, here we'll do it this way, omega equals change in theta over change in time. You know regular velocity equals change in distance or displacement over change in time. Well, you know that velocity, your change in distance around a circle is just r theta over delta t. And if we look at this, r delta theta, this piece right here, delta theta, is just omega. So two relations you need, v is equal to r omega, and omega is just your change in theta over change in time. Likewise, we can define alpha, which is your angular acceleration. This is in radians per second squared. This would be change in omega over change in time, alpha. So if you know that v, or change in v over change in time, is your linear acceleration, this is equal to r delta omega over delta t, and you get angular or regular acceleration, linear acceleration, is equal to r times your angular acceleration. So those are the two relationships you need from here. Now let's relate a couple of different quantities. So this is another strange little derivation. If this is some angle theta, and you draw your radius triangle, we're going to give you the formula for centripetal acceleration. So if you're going around this path, if there was no acceleration, you would fly off. But since there is, the acceleration is always going to point towards the center, and we call this centripetal acceleration. That means acceleration towards the center. So let's make a couple little triangles real fast. And if we look at this radius triangle, we've got R1, R2, so this is delta R, R1, R2, change in position. Let's draw a velocity triangle. You've got original velocity, velocity 2, the angle here theta, and this would be delta V. This angle would be theta as well. This triangle and this triangle have the same angle, they are similar. So if we compare this, we get delta R over R equals delta V over V. This is just because this triangle and this triangle are similar, same angles. So if we look at these, let's divide these by time. So we'll get delta r over r delta t equals delta v over v delta t. Let's move this v over here. So now we have v delta r, change in position over delta time, over r equals acceleration. In this case, this is your acceleration towards the center, your centripetal acceleration. And if you'll notice this right here, this is also just v. So you wind up with the expression where your centripetal acceleration equals v squared over r. You're going to be using this relationship a lot. So ask questions if you have any, well, ask me questions. If you ask YouTube questions, it doesn't really answer. But please, let me know. Now we've established angular quantities. In this case, delta x goes to theta, v goes to omega, a goes to alpha. Pretty much you replace all of these 1D motion things with squiggly letters, is how I like to say it. So everything you learned about 1D motion can be applied to 1D rotational motion. So let's work a couple problems. So if we're going to look at this, you're looking for a CD to spin from rest, so your omega naught is 0. Your omega, 300 RPM. So this is 300 revolutions per minute. Now you need to convert this, so there are 2 pi radians per revolution, and there are, in 1 minute, there are 60 seconds. 60 seconds. And this is going to equal 31.4 radians per second. Your acceleration is 130 rad per second squared, and your time's question mark. So what you'll do, you will use the exact same question. You don't know any of these, so we'll use omega equals omega naught plus, alpha t. You know your omega naught is 0, so you get omega over alpha equals t, which equals 31.4 rad per second over 130 radians per second squared, and you should get 0.242 seconds, just like one-dimensional motion problems. All right, let's work another one real quick. So if we look at this problem, we're finding the angular acceleration of a merry-go-round. So it makes 2 rotations while accelerating, so that would be theta initial starting at 0, and this would be 2 rotations, so 2 revolutions, and you know that each revolution is 2 pi radians per revolution, so this is equal to 4 pi. Omega naught, you start at rest with 0, you go to 1.00 radians per second. You're trying to find acceleration and you don't know time. So which equation do we use? Well, we look through this and we get omega squared equals omega naught squared plus 2 alpha delta theta. Now we look at this and we know that omega naught is 0, so we get omega squared equals 2 alpha delta theta. We are solving for alpha, so if we solve for alpha, we get omega squared over 2 delta theta equals 1 squared over 2 times 4 pi equals alpha, which is equal to 0.0398. I'm just going to round this. Alpha equal 0.04 radians per second squared. And that's it.